Okay? The goal of my talk is twofold. First goal, and it is the main goal, is to show that higher topological quantum field theory is a unifying concept in mathematics and physics. So it's my first goal. So when we will study particular mathematical problems, we would see that it is a particular case of a problem in higher topological quantum field theory. And second goal would be to provide simple examples. And I call them from enumerative geometry. So the advantage of examples from enumerative geometry is that you may see them. When I'll write you some formula, it is a formula. You cannot see it. It deserves some training to appreciate it. But when you see a problem in enumerative geometry, it's simple. You can imagine. But my first point, my first topic would be figures and differential forms. So, and the proper mathematical reference is BOT2 differential forms and their applications in, I forgot, in topology. So it's a famous book where everything is worked out with a proper mathematical precision. However, I will not give you a 10 or 15 lectures on it. I will just like to illustrate it, what I'm saying, by pictures. Okay, topic 1.1. Figures. Suppose you have a space X. Point. It's a figure. Curve. Figure. Disk. Also figure. On the space of figures, we may say that, okay, before I go further, I'd like to say the following. Assume that X is oriented. And figures are also oriented. It's interesting that there is no such a concept of orientation of a point. We will come back to it in a moment. But we know what does it mean to orient a curve connecting A and B. You choose direction. Like this or like this. We say that gamma 1 and gamma 2 are oppositely oriented. Now, we can generalize to disk. Here I have two identical disks. And here is something like a local basis. So I would say that D1 and D2 are oppositely oriented. Well, now let me construct an abelian group of figures. It means that element of fig is formal linear combination of Ci figure I. Ci are just numbers. You may say that Ci belong to Z, or Ci belong to Q, or Ci belong to real numbers, or Ci belong to complex numbers. Now I would like to impose the following relation. Figure. And here I have a change of orientation. Is minus figure. In particular, it means that AB is minus AB. Okay. Now, there is an important concept. the boundary. I can give a rigorous definition, but you may give it by yourself. I just want to say that the boundary of A going to B is B as a point minus A. I can have minus here. It is allowed in the abelian group that I am studying. In particular, the boundary of AB is A minus B or minus boundary of A going to B minus B minus A. And here I get the same A minus B. So it works. I will not waste time on explaining how to define it in multiple dimensions. Okay? The main property of the boundary operation is d squared equals to 0. Example. Consider triangle. Boundary of triangle is the sum of edges is AB. Here it's not a vector. Here I'm just writing down orientation. Plus BC plus CA. Depicted in this picture. Boundary square applied to triangle is B minus A plus C minus B plus A minus C. Yes, it is 0. Now, consider functions on X. There is very important thing that physicists never study, but all mathematicians study. It's called evaluation map. It has two arguments. It has points times functions and that gives numbers. So let me consider functions x going to r for simplicity. So I have points functions, and the result goes to r. It takes a point P and function f and brings the value of the function at point P. This may be easily generalized to linear combinations of points. So I would say zero figures So zero figures are combinations Ci, Pi, and function f. And it goes to sum of I, Ci, f of Pi. So what do I have here? I have a map between two linear spaces. This map is non-degenerate. So I may say that functions are dual to zero figures. Now, zero figures are a particular class of figures. So I'm looking for something dual to all figures. So I'd like to have something like this: figures, something, numbers. And I would like so this star is differential forms. And here I put an exclamation mark. So it is one of the definitions. So now let us see how it goes. Suppose we have a curve, gamma, oriented. We may cut it into small intervals, oriented. So would be differential form is just a map taking tangent vector, sorry, to a number, and we will assume this map to be linear. So this is cotangent vector depending on a point. And this is one form. Let us write it in coordinates. Let x mu be coordinates on x. There is a tangent vector that I will write as dr over dx mu. In the language of external geometry. You see, here my goal is to explain and not to give a minimalistic definition. So here I assume that x is embedded in some space Rn. And x is actually described by a radius vector. r depending on x1, xd. So there is a tangent vector. So I change parameterization x a little bit. And I am moving on the space x. And that's why this is a tangent vector. I just take derivative. In abstract setting, people forget r of x1, xd, and just say that there is a vector field. D over dx mu. Understood as derivative of the algebra of functions. But this is an algebraic point of view. So anyway, if you know just a little bit of differential geometry, you will understand that dr over dx mu is a tangent vector that I will call E mu. Now, I have a linear function sorry, now I consider I'm sorry. Dual object that I'll call U nu, such that U nu applied to E mu equals delta nu mu. Thus, would be one forms are linear combinations of U's omega nu of x times U nu, okay? Here I have omega nu of x u nu, and I can apply it to a tangent vector V. And the result is omega nu text naught. And here I have V nu x naught. If V is V nu x naught, and here is the basis E nu. Okay? So these are differential forms. Now, what is evaluation? I take this object, and now I'd like to pair it with something. So here is my curve gamma. What is this small vector? This is, of course, d gamma over d tau delta tau. So gamma is gamma of tau. So how can I understand this? D gamma over d tau. It is d gamma that depend on x on tau, and here I have tau. So it is d gamma over dx mu. Here I have dx mu over d tau. So I just plug it here, and I will get finally the following expression. Note that this is nothing but E mu. And this object is known as an integral of omega over gamma. Clearly, it is independent of parameterization, gamma of tau. It has multidimensional generalization. So gamma would be replaced by a fig, that is again gamma that depends on tau 1, tau k. K-dimensional figure. One can easily convince himself that differential forms become omega nu 1 nu k, u nu 1, u nu k. And the integral over the figure of omega would be integral over d tau 1 d tau k omega nu 1 nu k dx nu 1 over d tau 1 dx nu k over d tau k. Here, of course, x nu of tau 1 tau k is a parameterized description of a figure. Important remark. Nu would be antisymmetric. And this is known as an integral of the second kind. At least it was like this in Russian school textbooks. Okay. Important remark. Geometrical differential forms understood as linear functionals on figures are in one-to-one correspondence with algebraic differential forms. Understood as functions on t shifted by one x. In simple terms, omega nu1 nu k of x, psi nu1 psi nu k. Here psi nu are odd coordinates on the fiber. It's interesting. We have two definitions and they happen to coincide. Moreover, we may define the operation d star. What does it mean? Evaluation of figure n d star of omega equals evaluation of d figure omega. It is a definition of d star. From this definition, it follows that d star square equals to 0. Tim, is it clear why it follows?
Yes. We just transfer it twice and have d squared of any figures.
We just not transpose, we just conjugate twice. Now there is a great theorem. It's called seven authors theorem. So my explanation follows Arnold. Mathematical methods in classical mechanics. Part 2. So Arnold actually wrote a book on mathematical methods in classical mechanics. However, it has a section 2 or part 2, where he explained his point of view on on differential forms, and I followed his presentation. Okay, so Arnold was a great mathematician, and it's not a shame to follow his presentation. So great theorem is called seven authors theorem, and it is this. When properly presented, great theorems look like a very simple equation. And let us write down these seven authors. Newton, Leibniz, Green, Cauchy. I think it's like this. Gauss, 1, 2, 3, 4, 5. Ostrogradsky, Stokes. Okay, at least one Russian. So these great people proved particular cases of this theory. That's why it's called seven authors theory. You may ask, in particular, what Newton and Leibniz have to do in this company. They prove the following theorem. F prime dx from A to B is f of B minus f of A. So what is this? It is d dRam of f. It is a one form and could be integrated over an interval. And here the theorem says that this is evaluation of f and the boundary of the interval. But this is exactly evaluation of d star of f. AB. Okay? So that's what I wanted to tell you about 2 points of view on differential form. So you were criticizing me for going too fast and for giving hard lectures. So here I'm giving easy lecture. And then I will say more. Okay, I will not write it. After the break, I will say more about this evaluation considered as a pairing. Okay? So what I just told you is an interesting relation between super mathematics and geometry. I want to say more about this relation without hurrying up, okay? Recall that differential forms on X form an algebra. So we may expect an algebra on figures. So that's why I'm going to explain to you what is so-called Poincaré duality. So what it is all about? I have X. I can take two differential forms. I can multiply them and integrate. I would like to have something like this on figures. Namely, I will go in two steps. Step one. I would like to associate to a figure that I'll call Z, called chain. So chain is another name for a figure. A differential form, omega Z. With a property that integral over Z of omega is an integral over X of omega Z times omega. This multiplication is understood as a multiplication in the ring of functions of x and psi. Step 2. I would like to ask, what is omega z1 times omega z2? Okay, so here I am constantly playing on relation between algebra one is geometric and another is algebraic. I get more understanding on what's going on. So let me start with simplest examples. Let x be just r, okay? It's the simplest thing that I can imagine. What are figures on R? Points and intervals. Okay? Surprisingly, let me start with an interval. I, that is AB. So I'm looking for the following formula. Integral of R, omega I, and here I should have a one form. Would be equal to the integral over an integral AB of omega 1/4. Interestingly, I cannot find such omega I in the space of smooth forms. Instead, I can have an approximate omega I epsilon such that omega I epsilon is smooth Now it is clear how to find this omega I epsilon. This omega I epsilon should be a 0 form. Yeah. It should be just a function. And this function is easy to guess. I will draw it. You see, when it comes to geometry, I will draw pictures. When it is about algebra, I am writing down formulas.
Wait, we're integrating over an interval, so it should be a 1 form. Or am I missing something?
Yes, you are missing something. Omega I epsilon should be a 0 form. Omega 1 is a 1 form.
Oh, sorry. I thought,
That's why I explicitly, so in order to avoid this equation, I explicitly put 1 in omega 1. So this is omega I epsilon. You see, when it comes to geometry, you just need to look at the picture and you will see what happens. So it is smoothed theta function. X minus b minus theta of x minus a, probably with the opposite side. Is smoothed this thing. Okay? Epsilon equal to 0 limit could be drawn up. A, B, 1. It's not a problem. Okay? So this problem was solved. Now, another type of another figure. A point P. And now here we have a function. So this should be one form. This should be a function. A 0 form. And this is f of p, that it's an integral of p over f. And of course, you imagine that the result is a delta function. Something like this. With this length being epsilon, and with this height being 1 over epsilon. Let me call this delta epsilon. So it's how delta epsilon looks like. So omega p of epsilon is delta epsilon times dx. Here again, I know that psi is psi d over dx applied to x, this dx. So in the literature, people use dx. But people who are using dx are not super mathematics. They are not super mathematicians. They are mathematicians. In super mathematics, we use psi. Okay, we solve this problem. Now, exercise. What would happen if we apply d to omega of z? Let us use the main theorem. So should I assume that? So let me assume that x is compact. Okay, probably with the sign minus. And this is an integral of z plus epsilon corrections. So when I say plus epsilon corrections, I will write it O of epsilon. Now, what can I say about it? It is by definition. Okay, so there is a minus. Okay.
We should integrate this with omega.
Well, yes, so everything is written. 1 second. Right. So we have an interesting remark. I want you to see everything.
Can you explain a second step? Is that because x has no boundary?
Yes, it's because X has no boundary. So now let us come to our example. And it is exactly what we see here. When you take a DRAM, when you apply DRAM to this expression, you of course have minus delta at point B plus delta at point A. It's an illustration. You see, I prefer to have deep concept and simple examples than to have simple concept and complicated examples. So as a physicist, I will say that's how it works. So what have we gained? In dimension of x equal to 1, we constructed a epsilon map between figures and differential forms. You see, I'm constantly pushing this relation between figures and differential forms, relation between algebra and geometry. In mathematics, it's the main topic. So when people were asking what mathematics is, people used to say it's about figures and numbers. Two things. There are two things that we study in mathematics: figures and numbers. It was the old definition of what mathematics is. So what is the greatest achievement? The greatest achievement was to say that they are not different. There is some concept that we sometimes see as numbers, sometimes see as figures. And that's what all algebraic geometry is all about. And that's what Maxim Lenzon is teaching you about. We have two eyes in our brain. One is geometrical vision, and another is algebraic vision. And it is very unclear that it is the same. So I'm teaching you the stereo vision of mathematics in simplest example. So when we say algebra, commutative associative algebra, it's like a number. Okay, supercommutative associative algebra, it's again about numbers. It is a generalization of the concept of number. But we also have figures. Figures are still there. Now let us go to dimension of x equals to 2. So if we will understand what does it mean in dimension of x equals to 2, we will get it. Okay? Because it will be easy to generalize from dimension 2 to any other dimension. So, easiest thing is a point. And it is almost clear to a point in the xy plane. We associate to the point delta function of x minus x naught, delta function epsilon of y minus y naught, dx dy. All right? We consider an integral. And let me call it omega p epsilon. Over the plane R2. And here it equals to f of x naught y naught plus O epsilon corrections. So it was easy. Now let me consider P being a square. Sorry, figure. I'll call it Z. So omega Z epsilon is A, B, C, D. is a product of theta function. Theta of x minus b minus theta of x minus a, epsilon smoothed, y minus c, y minus c, y minus d. Not a problem. However, what corresponds to an interval? X, y, y not, a, b. Let me check, yes. So what corresponds to an interval? Integral over R2 of a 1/4 I hope that it's not hard to guess what it is. Tim, is it easy to guess it right now?
Yes.
So what it is?
It's a delta function over y and the difference of theta functions over x.
Delta functions but it should be one form.
Oh, yeah. So it's times dy.
Okay, great. So if we can do it this way, we understand the general structure. So what is omega associated to some curve epsilon?
Well, we studied it, what, 2 lectures ago? Using the multi-equivalent.
Okay,
Formula.
multi-equivalent is kind of a great formula. Okay, but I want you to understand it before multi-equivalent. So multi-equivalent is kind of algebraic view. And here we study geometrical view.
Well, we can split it into regions, and in those regions, define
Yes,
it as a,
exactly.
say, y is a function of x, or x is a function of y.
Split it into regions. And of course, here we use linearity. Like omega associated to z1 plus z2 is of course omega z1 epsilon plus omega z2 epsilon, right? So we can split into regions. Z1, Z2, etc., Zn. And it is enough to get omega epsilon of Z1. Here, we may take a local coordinates where Z1 is corresponds to y1 equals constant, right? Like here. And right. I can even put here zeros. Times difference of thetas. Okay?
That wouldn't give us what we want. We expect an integral over z1 of 1 to be equal to the length of the interval.
Why the length? I never used the concept length.
No, I mean, if we integrate just 1 over the...
So it means that for any function, so how should I write it? There are local coordinates in which
We should just use that formula from above, but
yes,
instead of y0, or what was that fixed value of y, we should put y of x as a function.
okay,
And that multiple integral is correctly defined.
okay. So Tim says it even better. That's why if a curve is y is some function phi of x. Okay? So Tim says that we just need to write down this thing, dy. But it also has a length in x direction. So this is omega epsilon corresponding to a curve gamma. Okay? And here we have O of epsilon. Okay, so you see what we have constructed. And so on in higher dimensions. Thus, we constructed a map. From figures to differential forms. Okay? And now, let us use algebra again. On the space of differential forms, we have a multiplication, right? So after we have done this, we may ask a question. I can even put epsilon 1 and epsilon 2. What does this thing mean? Is it omega of something? What is this question mark? Isn't it an interesting question? Connecting algebra and geometry together. And could you guess? What could it be?
Intersection?
Yes, great. It's an intersection.
Well, not really, because if we take, say, this omega, if we take z1 and z2 equal, well, if we take them equal, say equal to a point, 1 point, then we have like a product of delta functions, which is actually not a form of the right
Okay.
rank. It's
Okay.
so it's a bit more complicated.
Now we come to important question. Degree in psi's in the left-hand side is codimension of z1 plus codimension of z2. So for fixed epsilon, if codimension of z1 plus codimension of z2 is bigger than x, we have 0. So that's why point does not intersect with a point.
Wait, what do you mean? We have 0, 0 on the left-hand side or on the right-hand side, or
On the left-hand side, we don't know what it is on the right-hand side. On the left-hand side, so let us, you see, we have,
yeah, all right, that's clear. Yeah.
we have delta of p. Sorry, misprint. Omega of p. That is delta epsilon. I explained what delta is. Of p times dx. We have omega of p prime times dx. If I multiply these, I will get 0. For all p and p prime. However, what I can do, I can multiply these two. And I will get, of course, what? If p belongs to the interval plus O of epsilon, or 0 if p does not belong to an interval. So it is an intersection of a point and an interval. More interesting case is, of course, case R2. And this is the key figure. So algebra and geometry are neatly connected. And algebraic structure in algebra, what do we know about numbers? That we can add them and we can multiply them. So adding numbers correspond to taking figures into pieces, okay? While multiplying them means intersecting them. So this almost completes the classical dictionary. between algebra and geometry. According to advice of Bitcoiner, I decided not to rush and to explain this in detail. Tim, okay? Wasn't it too slow?
It was very clear.
Okay.
That's good, at least for me.
So please keep this picture in your mind on the unification theme of mathematics. And let me say some words. That there is a concept called derived algebraic geometry. And as the concept that is derived algebraic geometry, you actually can intersect point with a point. And in this case, you will get a manifold of an odd dimension. But I am not going to discuss it right now. So I think that first you need to have a classical picture in your mind, right? And the derived picture would appear later. Okay. So I will use this as a tool in examples of higher topological theories later on. I will use this correspondence, omega. So, any questions while I am copying the file?
So what's the resolution of this problem of intersecting a point with itself?
Okay, you want to know something in advance.
I mean, if we're gonna
Okay,
okay.
The resolution of the problem of intersecting of point with itself is to replace the point as a super algebra with differential. And then it will be possible to intersect to consider an intersection on the space of superalgebra, and then compute cohomology. And what you will find would be a manifold of a negative dimension. But we are not afraid of it. It would be a supermanifold. But I don't want to go that far right now. In the classical picture that I presented, all dimensions were positive. All codimensions were positive. And I never mentioned anything like manifolds of negative dimensions. But in super mathematics, we have them. But in classical, so what I explained to you was classical mathematics. Okay, in this case, let me tell you some interesting thing in advance. Okay? Maybe at some moment you would like it. There are pure spinors in C16. there is a cone of pure spinors. And you may consider intersection of a point with this cone. Interestingly enough, that naively you get nothing. Like in Tim's example. So you may intersect, classically, you may intersect a point only with something of the top dimension. However, if you intersect this point with a regular point of a cone, you get a space whose coordinate ring is an external algebra. And this is purely odd dimensional space. Moreover, if you intersect a point with a tip of the cone, you'll get polarizations of super Young-Mills theory. And all this happens in derived geometry. But I am not ready to discuss derived geometry before I discuss classical geometry. I will call it for future. Okay? So Tim's question of how to intersect a point with a point is not that stupid as you may think. Classically, it's zero. I want to be honest with you. But class is not over until I send you the notes, right? I actually want to enjoy relations between algebra and geometry.